Hello everyone. Welcome to today's live interactive session on geology and soil mechanics. Today we will be discussing on the third week lectures. The third week lectures were mainly based upon the topic of compaction. So we will be discussing on that, and then we will be solving some problems from the compaction topic. In the first session, as you might have attended, we had discussed the basic as the basic soil properties, the index properties, and then we solved some problems from those part. And in the second session, that is in the previous session, we discussed the soil classification topic in very detail. So we discussed the classification in a very detailed manner, and we solved a lot of problems from that topic too. And I uh, hope that soil classification uh, is very clear to you now, and you should be able to solve all the problems yourselves because we solved approximately 10 to 12 problems in the previous class, and all those problems covered all the various cases, most of the cases that are possible from the soil classification chapter, right? So I'm hopeful that you will be able to answer those. Any if any other questions also is asked to you from that part, you will be able to answer those. In today's session, we will be discussing about the soil compaction topic, and I will just discuss a bit at the beginning, and then after that we will be solving some problems. All right. So let us start the session. Right. So what is soil compaction, and why do we actually need soil compaction? So soil compaction is nothing but a process by which we densify the loose soil, right? Soil compaction is a process which we do so that the soil at a particular place can be densified. So we have a loose soil, we want to densify the soil, right? So why do we need to densify the soil? Say we are carrying some amount of soil from one place. So if you remember, if you can recall, we solved some borrow pit problems, right? Borrow pit problems from some place else. We were borrowing some soil, and then we are carrying it to the site, and with that soil we had to construct an embankment. And for that embankment has a distinct uh, density in which we need to put the soil so that we can construct that embankment, isn't it? So for that, what we need to do, when we bring the soil from that side, from the border pit, we need to compact it in a certain way so that we can construct the embankment. So it may be embankment, or it may be earth dam, or any other soil structure. Okay, that's why we need soil compaction. So what do we actually need to determine? We need to determine the number of passes of roller and quantity of water to be mixed. That is the number of the passes of the roller. The number of passes means number of times the roller, the road roller, you might have seen in the construction site while you drive around the road. You might have seen that there are rollers, right? They have huge drum kind of thing fixed at the front and the rear end, or sometimes only at the front end, right? So we need to determine the number of times that road roller we need to pass over that soil in order to achieve a particular amount of compaction or a particular amount of densification, okay, or the density of soil, right? And over that we also need to determine how much water we need to mix with that soil, so that we can densify that soil properly. All right, so both of these things we need to determine. Okay, both of these things we need to determine. All right. Okay, now let us see what is compaction. Compaction is the densification of soil by removal of air, right? We need to remove the air, and in that process what we are doing, we are densifying the soil, right? So we have to put some mechanical compactive effort, or you need to put some mechanical energy from our end, so that the soil actually, the soil particles get closely packed with each other, and the air, okay, the air actually gets removed. So that process needs some mechanical energy, and that mechanical energy is generally provided with the help of rollers. Okay, rollers in the field during construction, we need to provide that mechanical energy with the help of rollers. Okay, water is added to the soil during compaction, which acts as a lubricant. This helps the soil particle to come close to each other and obtain a better packing. So the water that we need to use, that water actually acts as a lubricating material. It lubricates the soil particles, so that the soil particles are easily able to slide about each other and attain a denser packing, right? Denser packing. That is the use of water. But there is a thing here. But beyond a certain point, the water starts replacing the soil particles and occupy the space. This reduces the dry unit weight. So if you if you plot the maximum dry density, okay, not the maximum, dry density, the dry density, and here we will plot the water content. Okay, so you will obtain a bell like curve. Okay, so initially as you pour water, the lubricating effect will aid in the densification of the soil, right? So what will happen, the dry density of the soil will increase, and then it will reach to a maximum point. But after this point, what happens, more the water you add, that water is going to replace the soil particles in a particular volume of soil. So due to that, what is going to happen, the dry density is going to reduce. Okay, so you obtain a bell curve like this. So the maximum dry density that is achieved, it is called the maximum dry density, MDD, and the water content at which this maximum dry density is achieved is called the optimum moisture content or optimum water content. Okay, I have also written it in the next slide. You can see the water content at which the maximum dry unit weight is obtained is called the optimum moisture content. Okay, and how can we determine the optimum moisture content of a particular soil? That we do with the help of a standard Proctor test. Okay, we take the help of a test called the standard Proctor test. We do that test to determine the OMC. So in the standard Proctor test, we have a mold like this. We have a mold. Okay, the volume of the mold is 944 cc. These are the values for standard Proctor test. For Indian standard Proctor test, the these values are a little bit different. Okay, so I suggest you go to the books or to go to the IS code which deals with this test. There you will find all the details. Okay, standard Proctor test. So we have a mold of 944 cc volume, and the dia is given here. Dia of this mold is also written here. So what we need to do, we need to put soil in three equal layers. We need to fill the soil in three equal layers in this mold. For each layer of soil, we need to put some amount of compactive effort, and that compactive effort is 25 number of blows. Now how to provide that, how will we giving those 25 number of blows those 25 number of blows will be given to each layer of the soil with the help of this hammer. This hammer is a standard weight of 2.5 kilograms. So what we do, we put the hammer over the soil, we pull it, and then we release it. pull it and then we release it. Okay, so this height of fall of this hammer is 30.5 kg. So this is how much potential energy you are releasing, that is fixed, standardized, that is from a height of 30.5 centimeter you are releasing a 2.5 kg hammer. Okay, so like the 25 number of blows you need to give for one layer, then again you put one more layer of soil, then again you put 25 number of blows, then again you put one more layer of soil, then again you put 25 number. Okay, after that you remove this cap and then you trim out the top. Okay, trim out the top so that the soil is level with the level with the top of the mold. Okay, so what we do, we first calculate the moist unit weight from the volume of the mold and the weight of the soil. So we measure how much weight of the, so initially you can measure the weight of the empty weight of that mold, and then after you put the soil, trim it off, then also you can measure the weight of the mold plus the weight of the soil. From that, if you deduct the weight of the mold, you will get the moist weight of the soil, right? You will get the moist weight of the soil. Now that moist weight of the soil, if you divide it by the volume of the mold, you are going to get the moist unit weight of the soil. You are going to get the moist unit weight of the soil. Okay, so moist is nothing but weight of the moist soil by the volume of the mold, right? Volume of the mold. After that, we need to calculate the dry density. So you already know how we can calculate the dry density from the total unit weight. How? So dry density is nothing but the total unit weight is a moist unit weight divided by 1 plus the water content. And what you do, from in that soil, you take some sample and then you keep it in the oven and take out the water content. Okay, take out the water content. Okay, take out the value so that you can calculate the dry density. So like that, for a particular amount of water content, you get a particular dry density. Now next, what you need to do, you need to mix some amount of water with that soil mass again, and then again put the soil layer by layer into the mold. Okay, so similarly again you will get one more dry density corresponding to one more water content. Like this you will get dry densities corresponding to various levels of water content. After that you can plot the curves. From there you can get the maximum dry density and the optimum moisture content. Okay, now for a given moisture content and moisture content and degree of saturation, the dry unit weight can be represented as what? I is equal to Gs gamma W by 1 plus E. Right, this is the standard formula for relation for dry unit weight. Now also we have what? Se equal to W into Gs. This also we know. So if we replace E with that, we will get Gs gamma W by 1 plus WGS by S. Okay, this is one more relation that we can obtain. Right? Now, for a full compaction, there should not be any voids present in the air, right? For a full compaction means theoretically when you have achieved a complete compaction of the soil, theoretically you have achieved the complete perfect compaction of the soil. That means what? That means air voids in that soil is zero, isn't it? Means theoretically you have achieved the maximum compaction, 100% compaction. Means what? You have eliminated all the air voids in that soil, right? The air voids are zero. In that case, only soil, solids and water will be present, isn't it? So air you have eliminated, so generally what? The soil is a three-phase system, right? So by compaction, what you have done, you have eliminated this part, you have eliminated this part, right? And what happens during due to compaction, as you have eliminated the air, so what happens, the air, all the air words are expelled, so the volume reduces. Say the initial volume was this much, v1. Now the volume will be reduced to, volume of the complete soil mass will be reduced to this v2. Okay, this much you have eliminated by compaction, so the total volume is going to reduce. Hence, if you just, if you, now our soil is this is our soil, this part is forms our soil, so here you can call the soil is that soil is such that it is 100% saturated. Okay, soil is such that 100% saturated. So how can we get the maximum theoretical dry density that can be achieved from any compaction? So in practical, it is not possible that you will be able to eliminate all the air words. Some air words will are going to remain, but theoretically it's possible, right? So theoretically, this condition, how you can get, we can put s equal to 1, right? So this relation we already know. In this if we put s equal to 1, you will get this dry density known as the zero air void dry density. So this is the dry density, and you have the water content. This will plot like this. Okay, this is the zero air voids line, means theoretically zero air voids, there are no air voids. Okay, right? So assume various values of water content and put in the previous expression, this expression that we already discussed, to get the uh, this expression to get the zero air void line. Okay, right? So this is our zero air void curve. So you can see the zero air void curve. The zero air void curve will always be at some distance from the practical whatever maximum dry density that you have achieved. Okay, we cannot reach here completely. Always there will be some distance or the other. Okay, there will be some distance. Okay, you cannot eliminate the eliminate this distance completely. Okay, always there will be some distance. It cannot be zero, because this is a theoretical limit. You cannot achieve that practically. Okay. Yeah. So what are the factors that affect compaction? First is the effect of soil type. So the grain size distribution, of the soil, shape of soil grains, type of clay, etc. All these affect the compaction. Okay, affect the compaction. Say the shape of the soil grains are so say the what to say all the shape of the soil grains are angular, then the soil is going to behave something differently, right? If they are rounded, then they are going to act something differently. So that way the soil type affects the compaction. Now the next is the effect of compactive effort. Okay, effect of compactive effort. So what happens, so say this is the dry density, and there we have the water content, right? And this is what, this is the zero air void line that we discussed, zero air void. And say for a certain compactive effort, we get this this as the your what to say, the bell curve, the compaction curve. Okay, this is the compaction curve. Okay, say for the standard Proctor test, you get the standard Proctor test, you get this as the bell curve. Okay, from the standard Proctor test. standard proctor test. Now when you do a heavy compaction test, means you increase the, say, number of layers, and you increase the number of blows, say you increase the number of blows per layer, then what is going to happen? The curve is going to shift left and up, means this point is going to the maximum dry density point is going to shift left and up like this. Now it will be here. Okay, similarly as you go on increasing the compactive effort, it will go like this. So you can put one, join one line known as the line of optimums. Okay, okay, so as you increase the compactive effort, increase the compactive effort at lower water content, at lower moisture content, you are going to achieve a higher maximum dry density. Okay, that is the thing. Okay, that is the thing. Okay, now next let us see. Yeah, now there is one more proctor test known as the modified proctor test. The Indian standard codes, this is known as the Indian standard heavy compaction test, and these values are a little bit different in that. Okay, similar to the standard proctor test. Okay, so please see the Indian standard code for their values. These are the different values. Okay, and for Indian standard, and whatever is given in the Indian standards, that is a little bit different, slightly higher, 1000 cc. 941 Indian standard takes 1000 cc as the volume, like that, a little bit different. Because whenever you do the test to pertain to some standard code, and then you refer that code and then you do the test always. Okay, so in that you can see a volume of the mold is same as previous, dia is also same, number of blows are also same, but number of layers here are 5 number of layers. So before it was 3 in standard proctor test, but modified proctor test we need to put 5 number of layers. Okay, 5 number of layers. Also the hammer weight has now increased from 2.5 kg to 4.54 kg, and height of the fall is also increased to 42.7 centimeter. You can see, right? So more amount of compactive effort or more amount of mechanical energy you are going to put, so that you can compact it more. Compact it more. Okay, now how do you achieve this compaction in the field? Okay, how do we achieve the compaction in the field? For that we need to use rollers. We need to use rollers, as I said. So rollers are also of different types. Rollers are also of different types. So one is the smooth wheel roller, smooth drum rollers. You might have seen this type of rollers generally around you, when around you with construction sites, or in the when the roads are being constructed around you. You might have, this is the most common type of rollers that are generally visible around us. So you have two drums, one at the center, one drums, two drums in the front, two drums at the rear, one drum at the one long drum at the front of the roller. These are very heavy, and the drum heavy rollers, and they move over the soil to compact it, right? Move up the road to compact the material. Okay, so this is one type of roller. Then you have pneumatic rubber tire rollers. Pneumatic rubber tire rollers, they are pneumatic rubber tires are formed with pneumatic. So let us see some of the pictures here. Okay, let us see some of the pictures. Okay, pneumatic rubber tire roller. Yes, these are the pneumatic rubber tire rollers. Okay, okay, and the smooth drum roller, you already know. What this Google is shitting. Yeah, yeah, this kind of thing, huh? Drum roller, drum roller. Okay, drum roller. Then we have one more roller which is generally used for clay soil. Okay, generally they are used for clay soil. Okay, yeah, these are called sheep's foot roller. Okay, they have some kneading action. Kneading action, you know how you knead the dough while making, before you make a bread, you need to knead the dough, right? You need to knead the dough with hands. These kind of sheep foot rollers have kneading action. Okay, so hence they are very much useful for compaction of clay type soil. Okay, clay type soil. Okay, this is you are seeing it is for road paving, foundation construction, dam construction. They are compacting soils such as loam, silt, and clay. Okay, they have kneading action. So these are sheep's foot roller. Okay, and then also you have one more type of roller known as the vibratory roller. So they have a destabilizing mass which rotates inside the drum, and due to that there is it imparts some vibration. Okay, it imparts some vibration, and these vibratory rollers are very much useful for your sandy type of soil. Okay, sandy soil, these are very much useful. Okay, for sandy soil. Okay, we saw this. Okay, this is for sandy. Now specifications for field compaction. Okay, specifications for field compaction. So uh, say 90 to 95% of the maximum dry density that you determined in lab, that is generally is specified as what to be achieved in the actual field. So you do some test in the lab for that particular amount of soil, particular type of soil that you have to use in the field, and for that particular type of soil you determine the maximum dry density and optimum moisture content. Then you suggest that 90 to 95% of this dry density you need to achieve in the field. Okay, like that you uh, specify to the field contractors, like that. Okay, so what is relative compaction? Relative compaction, R percent, is nothing but dry density that is the field by the dry density in the lab. Okay, into 100. Okay, this is going to be the relative compaction. Okay, it's always about 90 to 95%. Generally it's about 90 to 95%. For granular soil, the amount of compaction is generally specified in terms of relative density. So relative density, please tell me what is relative density. We had already discussed this in the previous classes, right? So you should know what is relative density. Please tell me. Tell me the expression of relative density. Tell me the expression for relative density. Relative density is what? Emax minus E mean E natural by Emax minus E mean. Void ratio in the loosest state minus void ratio in the natural state by void ratio in the loosest state by void ratio in the densest state, right? Emax minus E natural by Emax minus E mean into 100%. So this is how we get a relative density. Okay, now how do you actually find this field, the density in the field? In the field, how do you calculate the density of the soil? So there are various processes or various field tests that you can do easily to determine the field unit weight. So what are those tests? Let's see. Those tests that are the sand cone method. So what is the sand cone method? The sand cone method, we use an inverted cone, we pour sand in that, and with the help of that we actually with the help of the sand of known specific gravity and density, we actually determine the density of the soil there, density of the soil in the field. Okay, we use sand for that. Another is the rubber balloon method, where you use inflated rubber balloon to determine the field unit weight. And then we have the nuclear method. So sand cone method is the cheapest and the most used, generally used method to determine the field unit weight. And all of you will be doing this test in your geotechnical or soil mechanics lab in your undergraduate course. All of us have done or will be doing this test. Okay, the sand cone method test. So let's see the sand cone method as per ASTM 1556, which is the ASTM American Standard Code of which defines the sand cone method. So let us see that. Sand cone device consists of a glass or a plastic jar with a metal cone attached at its top. So you can see if a jar, and the top of the jar we have a metal cone that is attached. The combined weight of the jar, so and if what we do, we fill sand here completely, we fill it. Okay, so combined weight of the jar plus cone plus sand is, we note it down first, it is W1. Okay, the combined weight of the jar, the cone, and the sand, with the sand, W1. Then in the field, what we do, we put a plate. Okay, I will show you a video. We put a plate, and then we put a plate or tray, with this tray with a circular hole in between the field, and then we excavate the soil with between that circular hole in the tray. Okay, so that all the soil that you excavate out, you can retain it on the tray itself. It should not be lost. Okay, then we excavate the soil. So vast weight of the moist soil from the hole. So as I said, you excavate the soil and you retain the soil in the tray itself. It should not be get lost. It should not get lost, because you need to take the weight of that soil. Okay, you need to take the weight of that soil. So then we take the weight of the soil. That weight of the soil is W2. Now from the water content of excavated soil, we need to find out the water content of that. So you excavate that soil. That soil you take the weight, also the moist weight you take. Also you calculate the water content of the soil. Okay. So the water content we got, from there we can use that, we can find the dry weight of the soil. So you can find W3, which is the dry unit of the soil, is nothing but W2 by 1 plus W is W% by 100. Okay, whatever you already know, similar to the dry unit weight. How you find a dry unit weight? Same, just unit weights are unit weights are replaced by weights here. Okay, after the cone sand filled jar, after that what you do, we have got a hole. Invert this particular jar with the cone into that hole, and then we open the valve here. So what happens, as soon as you open the valve here, sand is going to pour out and fill that hole fill that hole. Then you take the weight of the jar plus cone plus remaining sand in the jar, that you will get W4. The weight of the sand to fill the hole in the cone, then you can get, right. So some amount of sand will get inside the hole, and some more amount of sand will be filling that cone, which will be just over that hole as soon as you lift that jar from above it, right. So that, so weight of the sand to fill the hole in the cone will get W5. From there what we can do, we can calculate the volume of the excavated hole. How? Volume is equal to W5 minus WC. WC is nothing but the weight of the sand in the cone. That this weight of the sand in the cone you need to measure before and only in your lab. You put a glass plate, after over that you put the sand, invert this apparatus, then you open the valve, sand is going to come out, close the valve, move away the apparatus, then you measure that amount of sand, you will get the weight of the sand in the cone. So WC, so W5 minus WC divided by the dry unit of the sand. As I said, you need to know the dry unit of this particular sand that you are using. Divided by that, you will get the volume of the excavator easily. Right? So sand cone method, you can see this particular video. Okay, see this particular video where this sand cone method is discussed. If you go to YouTube, and if you want to, if you see that, let me just open it here. So you can see many videos are there. You can see any of the any of these videos to actually uh, see how this method works. Okay, any videos, several videos you can get in YouTube. Okay, see this is on this ads are. See, they are showing this test. Okay, how to do. So you can see there are many videos that are available over the internet. You can see these videos. So this is the plate I was talking about. This plate is a small hole in the center, and then you can see that. So when you excavate this, you pour out all the, yeah, you should retain that soil because it will take the weight of that soil. Okay, so like this you do. This is the apparent the calibrating cylinder, whatever, to calibrate the weight of the soil in the cone, all those stuff. Like this you just see. I'm not seeing this now. You see it later when you have free time. Many videos are available. You can see the videos. Okay, you can see the videos. Just give me a second, then we will discuss this permeability. Yeah. So, what is permeability? Water flows through soil due to the presence of interconnected voids. Void, right? So there are voids in the soil, as we already know now. That and these voids are, some of these voids are interconnected. Okay, interconnected. They form a channel, interconnected channel pathway. So water can flow through the soil through these pathways that are formed in the interconnected void. This flow occurs from point with high head to lower head, right? Obviously, it's going to flow from a point of higher head to lower head, and during that flow, some head loss occurs, right? Some head loss occurs in that process. So, say you have a soil mass like that. So here, and this is the datum. Okay, so this the head at this point is, say this is the point A, this is the point B. Okay, it's HA. The head at this point is HB. So obviously water is going to flow in this direction. Flow is this direction. So what we can do, if we know the length L, length of flow, we can write a gradient, hydraulic gradient. It is I. Is nothing but HA minus HB by L, but delta H by L. This is the hydraulic gradient. Okay, and what is this? This term is nothing but the head loss. So hydraulic gradient is nothing but head loss divided by the length of flow. Okay, length of flow. Now when the water flows through the soil or fluid flows through the soil, that the velocity of flow is extremely slow. The velocity of flow is extremely slow. So if I want to plot the velocity of flow to the gradient here, so it's generally linear. Okay, the velocity to the hydraulic gradient, this relation is generally linear. What's wrong with this? Okay, it's linear. Why is it linear? Because in this regime it is a laminar. We consider that the flow is laminar, and above this boundary the flow is turbulent. It's not at all linear in this region. Okay, but we consider that the flow in the soil happens in a regime that is laminar. Laminar flow happens. Laminar. What do you mean by laminar flow? Laminar flow means each of the layers of the water are flow independent to each other, and they do not interact to each other. Okay, so if they interact to each other, they become turbulent. So if you open your bathroom tap in the washroom, water flows are very fast, right? And that is kind of a turbulent flow. Okay, but if you uh, close the faucet a bit, you'll see that the water flows out very nicely in a cylindrical way. So that is kind of laminar flow. Okay, so you consider that the flow is laminar. So as the flow is laminar, we can write from Darcy's law that velocity of flow is proportional to the hydraulic gradient. Right? Velocity of flow, discharge or the discharge velocity. Okay, the discharge velocity is proportional to the hydraulic gradient. Okay, and this is valid only for laminar flow. All right, so V you can write into Ki. K is nothing but the what? Proportionality constant, right? K is the proportionality constant, which is known as the coefficient of permeability. It's known as the coefficient of permeability. Okay, K is the coefficient of permeability, and it depends on various factors. One of them is the soil type. Okay, one of them is the soil type. Okay. Yeah. Next we have seepage velocity. Okay, seepage velocity. So now say when the water is flowing, so say we have, this is the total volume. Okay, total volume V. We draw it a little bit properly. The total volume V. Indeed, that V some amount of volume. So let us consider this is a pipeline. Okay, say pipe. This is a pipeline. This is a pipe, cross section of a pipe. In that pipe, some area is taken by the soil solids, and then some area is taken by the voids, right? And this is the V is the complete volume, or the A is the cross sectional area, complete cross sectional area of our pipe. And in that pipe, some amount is covered by the solid, and some amount is taken by the voids. Now VV we know is nothing but the volume of voids, and Vs is the volume of solids. Okay, now a flow Q, which is nothing but the flow. Q is the flow. This flow is what? The velocity of flow. The flow is nothing but the velocity times the area. Velocity times the area. So from the continuity equation we can write V velocity, area of the voids plus area of the solids, which not is equal to the, but the actual flow. But the actual flow occurs through what? It doesn't happen through the solid, right? It happens only through the voids. The actual flow happens only through the voids, right? Only through this part. Only through this part the actual flow happens. The velocity of solid level Vs, not velocity of solid. This is the seepage velocity. The seepage velocity times the volume of voids. Now from here I can get the seepage velocity, the superficial velocity is AV plus AS by AV. Okay. Now if you multiply with the length of the pipe, the length of the specimen, you can write like that. And so area multiplied by L is nothing but the volume. So volume of voids plus volume of solid by volume of voids. Right? From here I can again write V by V times 1 plus Vs by Vv. Vs by Vv is what? Now what is void ratio? Void ratio is what? Vv by Vs, right? But here we have Vs by Vv. So 1 by E. So 1 plus 1 by E I get, right? V into 1 plus 1 by E. Now Vs I can write as, from here I can write as V by N. N is what? N is the porosity. N is the porosity. So using the relation between E and N, I can write Vs equal to V by N. V by N, or V is equal to N into Vs. N into Vs. Now the porosity, what is the value of porosity? The value of porosity is always less than, will be always less than 1. Will be always less than 1. That means what? That means our superficial or the seepage velocity. The seepage velocity is always greater than V. The superficial velocity. The seepage velocity is always greater than the superficial velocity. Vs is the seepage velocity and V is the superficial velocity, which is considered by taking the complete area. But generally the flow only happens with the voids, right? So Vs is the actual velocity. So the Vs is always greater than the V. Okay, and the relation between them is they are related by the porosity. Okay, this is how we can derive the expression for the seepage velocity. Okay. Now let me see once what's there next. Okay, so V is the superficial velocity or the discharge. I will write it nicely. Don't know what's wrong with this. Yeah. Now, what are the factors, various factors that affect the hydraulic conductivity? One is the fluid viscosity. Obviously, if the fluid is more viscous, then the permeability will be reduced, right? Permeability will be reduced, and if the fluid is less viscous, then the permeability will be higher. That's how your hydraulic conductivity or the permeability is going to get affected by the fluid viscosity. Then you have temperature. So the temperature affects the what? Viscosity. So if temperature is higher, viscosity is going to decrease, like that, like you understand, right? So if temperature affects the viscosity, and then the viscosity is in turn going to affect the hydraulic conductivity or the permeability. Okay, then you have the pore size distribution, because you know the actual flow occurs through the pore network, right? Pore network. So the size of the pore, how the pores are distributed, those are going to affect the radial conductivity obviously. And gain size distribution, as I said, it's also going to affect. Void ratio again is a function of the pore size distribution, that is obviously going to affect hydroelectric conductivity. The roughness of mineral particles, so if the soil particles are rough, it's going to resist the flow of water through it, so it's going to affect the hydraulic conductivity. And then you have the degree of saturation also affecting the hydraulic saturation is higher, then hydraulic conductivity will be somewhat, and if it's less, the hydraulic conductivity will be somewhat different. So this is, so all these factors are actually affecting the hydraulic conductivity. Okay, so with this we will end, and next what we are going to do, we are going to start solving the problems. Okay, we will start solving the problems. Okay, so try to do this. So we have the compaction of a floor area is carried out in 250 mm thick layers. The hammer used for compaction has a foot area of 0.05 meters square, means the area of that hammer, the foot area where it's contacting the coming in contact with the soil, is 0.05 meter square. Okay, and 250 mm thick layers of soil we are compacting. Okay, the energy developed per drop of the hammer is 50 kg meter. Assume 35% more energy in each pass over the compacted area due to overlap. Calculate the number of passes required to develop compactivity equal to IS heavy compaction for each layer. Okay, first try to uh, find out the compactive energy as per the highest Indian standard heavy compaction. Try to do that. Means in Indian standard heavy compaction, which is similar to the modified tractor test, but the volumes and the heights are a little bit different. From there, using that, you need to find out the compactive energy that is imparted in a highest heavy compaction test, that you need to calculate first. Okay, so try to think for 1 minute, then I will solve. Try to think for a minute. See, see. Compactive energy for IS heavy compaction is, so 4.9 kg hammer. I am also writing the units in the bracket. 9 kg hammer, 450 mm drop, 5 number of layers times 25 number of blows. This divided by the volume I will do. Okay, 1000 cc to the time 1000 centimeter cubes, that I am converting to meter cube. Meter cube. That I will get 2756 2.5 kg force meter per meter cube. Okay, so this is the compactive energy per meter cube. Okay, now compactive energy per drop provided by the rammer that we are using per meter cube of soil is what? This is given in the question. 50 kg meters of energy, 50 divided by the volume. So it's 0.05 is the area and 250 mm is the thickness, into minus 3, nothing but 4000 kg force meter per meter cube. Okay, now I am to find out the number of passes required to develop. Okay, number of passes, but assume 30 given. So n into 1.35 for the 35% into 4000 is 27562.5. So from here n will come out as, calculate that how much annual number of passes you are getting. Calculate please. It's coming out as how much? It's coming out as 5.1. So 6 number of passes, 6 passes you can use. Okay, you can use 6 passes. Okay. Let us see the next problem. The following results were obtained from an IS Indian Standard Light Compaction Test on sample of soil. So these are the test results that we obtain from the Indian Standard Light Compaction Test. All right, the water contents are given and the mass of the moist soil is given in kgs, kilograms. Plot the compaction curve, obtain the optimum moisture content and the maximum dry density, calculate degree of saturation and the theoretical maximum dry density. Okay, so water content is given and the mass of moist soil is also given. So first what you can do, you find out the moist, you make a table. First of all, so one more information is given. G is 2.68. Okay, the specific gravity of soil solids is given 2.68. Now what you do, you can form a table, and in the table you can write out down all the quantities, and then so that it will be easier for us to calculate. So first we will write down the water contents. It is 0.12. These are not in percentage. Okay, these are in decimal. These are not percentages, these are the water contents. Okay, 0.15, 0.18, 0.21, 0.24. Okay, then we have the mass in kg. So what are the masses? 1.65, 1.95, 1.93, 1.90, 1.89. Now for the IS light compaction, industrial light compaction, what is the volume of the mold that you use? What is the volume of the mold that you use? That is 1000 cc's, 1000 centimeter cube, right? So easily you can calculate the moist density in gram per cc, because you have the mass in kg and you have the moist, you have the volume also, you know, is 1000. So this you can easily calculate in gram per cc. So just calculate this fast. What? Same, right? 1.65, 1.95, 1.93, 1.86, right? Next step is to find out the dry density. So dry density we already know. What is dry density? Dry density is the moist density divided by 1 plus the water content. So calculate the dry density similarly for all. Do that. What? So dry density is what? Dry density is moist by 1 plus water content. So just you need to do this. You'll get 1.47, 1.69. Okay. Now next task is to find out the, so with this amount of information I can plot our compaction curve, right? Because I know the water content, I know the dry density, I can plot the compaction curve and then obtain the optimum moisture content and the maximum dry density. Okay, so first, so this much I can do with this much information. Okay, but one more thing is also asked, calculate degree of saturation and theoretical maximum dry density. Now for calculating the degree of saturation and theoretical maximum dry density, so we know that the saturation is what? S is equal to Wg by E. So W I know, G I know, E I need to find out. E I need to find out first, so that I can find out the degree of saturation. Now what is the dry unit weight? Gs gamma W by 1 plus E. So from here I can get E is what? G gamma W by gamma D minus 1. So using that, so gamma here, all gammas are these are gammas, right? But here you can see the unit, so take care of the units while you do it. Okay, so for first case G is 2.68 times 1 divided by 1.47 minus 1. If you do, you will get the void ratio for the first one, which is 0.82. Similarly, you can calculate the void ratio for the others also, right? You can calculate the void ratio for the others also. So first one will be 0.82, then we will have 0.58, then we will have 0.60, then we will have 0.70, then we will have 0.79. Okay, 0.79. So EI got. Now from this relation I can easily get what? The S, the saturations I can get. You can get S is equal to 0.39, 0.69, 0.80, 0.804 and 0.81. Fine. Now the last task is to calculate the theoretical maximum dry density. Now what is the theoretical maximum dry density? So you know G gamma D, Gs gamma W by 1 plus E. So Gs gamma W 1 plus Wg by S. So if you put S equal to 1, you will get the theoretical maximum. So Gs gamma W, this will give us the theoretical maximum, right? Theoretical maximum. Just put all the values and you will get the theoretical maximum density. This will be 2.03, 1.91, 1.81, 1.71 and 1. Calculate this. Okay, how much I am unable to see. Okay, calculate this. Okay, 1 point something it will be. So you can see obviously this theoretical values are obviously what, more than this value, right? More than your this 6.3, I think. Okay, more than this whatever you calculated, the actual values. So obviously this theoretical will always be higher, theoretical densities will always be higher than the your whatever actually you are having. Okay, so then after that you can plot it easily. Okay, the this is the water content in this side, and this side we have the densities. Okay, so from here you can get the maximum dry density here, approximately say like this we will get. This is our optimum moisture content, and this is the maximum dry density. Okay, from here like this, after plotting you can get. Okay, now next problem is similar to this. The following results were obtained from a standard compaction test on a sample of soil. These are the values that are given. Water your content is in percentage, it's given in the in percentage terms now, and also you have the bulk unit weight or the moist unit weight. Plot the compaction curve, obtain the optimum moisture content and maximum dry density, and then you calculate the degree of saturation at the maximum MDT and plot the zero air voids time. So first what you do, first you calculate the dry densities corresponding previously how you did here. You calculated the from the moist, you calculated the dry densities, right? So here already the moist unit weights are given to you here. So directly you can calculate the dry densities. Okay, so directly please calculate the dry densities. Okay, let's calculate this. It's very easy. Directly you already know how to do. Let's do it. I'll give you a minute. So dry densities, what? Dry density is what? Easy, right? This is gamma moist by 1 plus W. That only that much you have to do. To 15.9. Alright, got that? So with this information, the water content and the dry density, you can plot the compaction curve and you can find out the optimum moisture content, maximum dry density. Next is the calculation of what? Degree of saturation at MDT. So first let me so when we plot the compaction curve, the blue one is the compaction curve. Okay, from here if I find out something like this, I will get our maximum dry density and the optimum moisture content. Okay, so the maximum dry density is approximately 18.4 unit per meter cube. Okay, now it is asked to us calculate the degree of saturation at the MDT. Now let us write the relation for the dry density. Right, so this is the relation that we have. G you can take as 2.6. We have a gamma d. From here we will put the maximum dry density, which we got as 18.4. So 18.4 is 2.68 times 1 by 1 plus, what is the optimum moisture content? This optimum moisture content we will put here by OMC times 2.68 by S. From here what you can do, you can get the degree of saturation. Okay, you can get the degree of saturation. Next is the zero air void line. How to get the plot the zero air void line? So you know this again. This is the expression for air void line. So change the values of this water content. For air will get different values of dry density. You will get, then you can easily plot this line. So this is our zero air void line. Okay, very easy. Let us see this. The maximum dry density of a sample by the standard compaction test is 1.76 gram per cc at an optimum moisture content of 14.5%. Okay, the maximum dry density of a sample by the standard compaction test is 1.76 gram per cc at an optimum moisture content of 14.5%. Find the air voids and the degree of saturation if the G, this is nothing but a specific gravity of soil solids, is 2.68. What is the theoretical maximum dry density at this optimum moisture content? Okay, so we need to find out what? We need to find out first, we need to find out the air voids, means Na percent, and the saturation, degree of saturation. These two things we need to find out first. Okay, what is given? The OMC is given as 14.5% and the maximum dry density is 1.76 gram per cc. Now there is a relation that relates the dry density to the air voids. I will write that relation. D is 1 minus Na by 100 Ts, W 1 plus W into Gs. So here I can put my values. So please calculate Na from this one. We do, we'll get the first thing, that is the air voids. So remember this relation. Remember this relation. This will come out as 0.088, which is nothing but 8.8%. Okay, 8.8%. Now the next task is to find out the saturation. So again we have this relation with us. Yes, so saturation I can get from this, right? Just here in place of our what to say, gamma D, I have to put what? I have to put my MDT. This is 1.76. GS I know 2.68. This is 1 plus optimum moisture content 0.145 into 2.68 by S. From here I can get the degree of saturation. Okay, I can get the degree of saturation. Okay, so please calculate this, right? Okay, next we have to find out the theoretical maximum dry density at this optimum moisture content. What is the theoretical maximum dry density at this moisture content? For that theoretical maximum we have GS, right? So GS again 2.68 times 1 by 1 plus 0.145 times 68 by 2 we will get 1.93 gram per cc. So at this much water content, this is the theoretical maximum dry density, but in actual case we are having a dry density of 1.76. So as I said, the actual maximum dry density will always be less than this, less than this theoretical maximum, right? So the actual dry density is always going to be lesser than this theoretical maximum dry density. Okay, now let us see this problem. As per compaction specification, a highway fill has to be compacted to 90% of Indian standard light compaction test dry density. 90% of the Indian standard light dry density that we get from the lab, 90% of that dry density we need to achieve in the while constructing the highway fill. A borrow pit available near the project site has a dry density of 1.78 gram per cc at 100% compaction and a void ratio of 0.63. Okay. Compute the volume of borrow material needed to construct a highway fill of height 5 meter and length 1.5 meter with a side slope of 1:2. The top width of the fill is 10.5 meter and G for the soil solids is given as 2.7. Okay, so let us do slowly. So first, the dry density for the borrow pit. Okay, let me write here. And the void ratio of the borrow pit is also given. Now, the density that is to be achieved in the fill. Okay, 90% of Indian standard light compaction test dry density means 90% of 1.78 we need to achieve. Okay, that is gram per cc. Now we have to construct a what? Construct a highway, and the size dimensions of the highway field is given. So the top width is 10.5 meters. Okay, length is given, height is given, height is 5 meter. Okay, this height is given 5 meter and the slope is also given 1:2. This, okay, the slopes are also same. Okay, 1:2. So I can find out this length, right? It is nothing but, so this is 10.5 plus 2 into, how much? This height is 5, so 10, 2 into 10, so it's going to be 30.5 meter, this total width. Okay, total width. Now, so therefore the what is, therefore now we can calculate the volume, so we know the dimension of the cross section as well as the length also we know it's given as 1.5 meter, so we can calculate the volume. Okay, half into sum of the parallel sides into height into the length. So this I am calculating in meter cube. One more thing, this is 1.5 kilometer, not meter. Kilometer. Okay, kilometer. That's why I'm multiplying by 1000. Thank you. Therefore, T fill is G into gamma W by 1 plus E fill. Now this one I know is 1.602. right? So from here I can calculate the E fill as 0.685. Now the next whatever we are going to do, that is similar to what we did in the uh, our first class, the borrow pit problems when we solved in the first discussion session. That is similar to that. Okay, so volume of solids will be same, right? The volume of solids that you are carrying from the borrow pit is going to be the same when you put it on your site. So volume of solids remain constant, so we'll represent we will equate the volume of solids. Okay, so volume of solids we are going to equate, so VV by 1 plus EV, that we fill by 1 plus fill. From here I can get VB water pit is equal to 1 plus EF, sorry, 1 plus EB na, plus EB by 1 plus F into BF. So from here I can get 1 plus 0.63 plus 1 plus 0.685 into 53750, 57486 meter cube. So what we are asked? We are asked to compute the amount of borrow material, right? So what is the amount of volume of borrow material that we need to bring to the site? Okay, so that is nothing but this 57486 meter cube. Okay. Okay. Next problem, in Indian standard light compaction test, bulk unit weight of soil sample is found to be 18 kilonewton per meter cube at a moisture content of 13%. Determine degree of saturation, additional moisture content for full saturation, maximum theoretical dye density. So first thing, the degree of saturation, this you can easily do, so just try to do that first. I will be back in a minute, just try to do that meanwhile. Try to do that, try to find out the degree of saturation. So directly just put the values, it's very easy, na? So gamma, uh, yeah, so gamma total is what? G into 1 plus W by 1 plus WG by G plus C. So into gamma W. So we have 18 . From here I can find the S, degree of saturation, think but 0.5356, which is equal to 53.56%. Now next is to find out the void ratio. The void ratio will be W into G by S. So 0.13 into 2.68 and 0.5356 is 0.65. So I found out the void ratio too. Okay. Then next task. Now see, at any given compactive effort, the void ratio actually remains the same. The void ratio actually remains the same, remains constant. Okay, the void ratio remains the constant. So I will write it down. At any given compactive effort, the E remains the constant. Okay, so S is what? WGS by E. Now if S is 1, we'll have WS E by G, which is nothing but W is equal to 0.65 by 2.68. Is it 0.242 or 24.2%? So at this much water content, this is the additional amount of water content that is required for us to achieve the full saturation. Achieve the full saturation. Okay, so understood, right? Achieve the full saturation. So additionally, (11.2%) water we need to put. So our soil is like this, right? So your soil solids, your water, your air. So we need to fill up this with water. Addition 11.2% is needed to fill up this with water, so that we get complete saturation. That's the thing, nothing else. And maximum theoretical dry you can easily find out now. You already know the relation. Just put the water content in that, and you find out the maximum theoretical dry unit weight that can be found, that is possible. Next, the in situ void ratio of a granular soil deposit is 0.59. The void ratio in the loosest and the densest state were found to be 0.81 and 0.37. Determine the relative density and the relative compaction of the soil deposit, which is 2.7. So first find out the relative density. It's very easy, one liner. You can easily find it out. So try to just calculate the relative density and tell me the answer first. Just calculate the relative density first. Calculate the relative density. So the void ratio in the loosest and the densest state are given. Loosest state means the E maximum is given as 0.81 and the E minimum, this is the void ratio in the densest state, it is 0.37. So you can calculate the relative density, right? The relative density is what? E max minus E natural by E max minus E min. So what is the natural density? Is given 0.59. So I can calculate 0.81 minus 0.59 by 0.81 minus 0.37 to 100%. So this will come out as 50%. The relative density of the soil, granular soil deposit, is 50%. Now next we need to find out the relative compaction, right? Relative compaction of the soil. What is the maximum dry density of the soil? G gamma W by 1 plus E mean, right? Minimum densest state. So 2.7 into 9.81 by 0.37. So this is coming out as 19.33 kilonewton per meter cube. This is the densest maximum dry density. Okay, maximum dry density. Now the maximum dry density, that is in situ is what? 2.7 into 9.81 by 1 plus now this 0.59, which is the 16.65 kilonewton per meter cube. Okay, per meter cube. Therefore the relative compaction is what? In situ by gamma d max but 86.13%. Okay. Now next problem. Now next problem is from permeability. For the soil specimen shown in the figure, calculate the soil permeability if the rate of flow is 2 centimeter cube per minute, 2 cc's per minute. The area of the cross section of the specimen is 8 centimeter square. This is extremely easy. Just try to try to do this. Try to solve this problem. So permeability you have to find out everything. All the details are given in the problem question to you. Do this, very easy. Everything is given, right? So from the Darcy's law, we know velocity is what? K into I, permeability times the hydraulic gradient. So flow is what? Velocity into area, which is nothing but KIA. So therefore, what is the this K permeability or hydraulic gradient? Q by I into A. Now what is Q? Q is given, the flow is given to 2 centimeter cube per minute. So 2. What is the hydraulic gradient? So hydraulic gradient is what? Head loss by the length of flow. So what is the head loss? 15 minus 5, because here left side head is 5, right side head is left side head is 15, right side head is 5. 15 minus 5, length of flow is how much? 12, right? So 10 by 12. So 10 by 12 times the area, it's what? 8 centimeters square is given. Simple. So this will come out as how much? Calculate this. 0.3 centimeter. What is the unit? Centimeter per minute. Okay, centimeter per minute. Since 2 is in centimeter per minute, centimeter per cube per minute, this will be in centimeter per minute. Okay. Similarly, try to do this now. Find the coefficient of permeability of a soil sample which has a height of 6 centimeter and cross-sectional area of 50 centimeter square. Water equal to 450 ml, 450 milliliters passes down through the soil sample in 10 minutes under an effective constant head of 40 centimeter. The oven dried weight of the specimen is 495 grams. Calculate the seepage velocity if the GS, that is the specific gravity of soil solids, is 2.65. So we need to find out the seepage velocity VS that we discussed earlier in today's session. That VS you need to find out. So obviously first you need to calculate the discharge velocity v. After then you need to calculate the n, that is the porosity, and v divided by n will give you the vs, that is the seepage velocity. So first of all, the first task is to find out, let us write down the flow. Okay, so flow is how much? It's given 450 ml milliliters passes the soluble in 10 minutes. So 450 ml divided by 10 minutes, this we convert to centimeter cube, and then to seconds it will come out as 0.75 centimeter cube per seconds. Okay, next, what is the hydraulic gradient? What is the hydraulic gradient? Under a constant head of 40 centimeter. So 40, head loss is, the head is 40, and the length of the specimen is 6 centimeters. So 6 is 6.67. Therefore again K I can find out similarly to the previous problem. Q by IA. Q is 0.75, I is 6.67 into 50. So it will come out as 2.25 into 10 to the power minus 3 centimeter per second. So we found out the permeability of the or the hydraulic conductivity of the soil. Now we can find out the discharge velocity V. What is discharge velocity V? V is nothing but K into I. So 2.25 into 10 to the power minus 3 into 6.67. Velocity times hydraulic gradient will give us the K hydraulic gradient times the what permeability is going to give us the velocity, discharge velocity. So this will come out as 0.015 centimeter per second. Right now, gamma d, what is the dry density that is given? Dry weight divided by the total volume. The dry weight of the soil sample is given as 495. So 495 divided by the volume. Volume is what? 50 is the cross sectional area given in the question. 50 is the cross sectional area and 6 is the height of the sample. So 50 times 6 will give us the volume. So it's 1.65 gram per cc. Now again we use that relation by 1 plus E. So 1.65 is 2.65 times gamma W by 1 plus E. From here I can get my E as 0.606. Now if I know the E, I can easily find out the N. I can easily find out what? The N. N is my, N is what? N is the porosity. So we know the relation between the porosity and the what? The porosity and the void ratio. So En is E by 1 plus E. So this will come out as 0.377. Therefore, the seepage velocity is nothing but V by N. Discharge velocity was, we calculated as 0.015. Here we calculated that, divided by N, 0.377. It's come out as 0.039 second. So you can see that this seepage velocity is obviously greater than the discharge velocity. Okay. Okay. Now let us come to the last problem. So for each of the cases 1 and 2 given in the figure below, determine the pressure head, elevation head, and the total head at the entry and exit. Entry and exit, and also at A point, the point marked as A on the sample. You can see in the figure A is marked on that sample. What are the superficial and seepage velocities of the flow? So what I'm going to do, I'm going to solve the first one, and the second one do it by yourself. Okay, the second problem will be homework. Okay, we'll solve it In the next class, in the beginning, we'll see if you are able to solve, and this will be a homework, and the first one I will be solving now for you. Okay, right? So what I am going to do, I am just going to make a table. So we are going to find the all the heads at all the distinct points that are marked in the figure. At all the distinct points that are marked in the figure, we are going to find out the all the heads, the pressure head, the elevation head, the total head, everything. Okay, so let us see. First, let us write out elevation point. Let us make a table. Elevation point, then we have elevation head in meters, then we have pressure head in meter, then we have total head in meter, then we have the head loss in meter. We will write all the points. Elevation point from this figure we will write elevation point 10, elevation point 6, elevation point 2, elevation point 0, and elevation point 3, which is nothing but our A point. Okay, A point. Okay, A point, this A point, huh? Elevation point 0, elevation point 6, elevation point 2, elevation point 0, and then also the A point. Okay, now what is the elevation? Elevation head is nothing but the distance from a datum. So here let us take this point as the datum. Okay, this is the datum. From this we need to find out the elevation or the height of our point in consideration, height of the point in consideration. So from here the elevation of the point number 10 is not 10 meters, right? Elevation of the point 6 is how much? 6 meters. Elevation of the point 2 is how much? 2 meters. Elevation of point 0 is 0 meters, and this elevation of the point A is what? 3 meters. So easy, just from the figure you can find out the elevation heads, all the elevation heads we found out. Next, at the point, this point, the elevation head is 10, but the pressure head is 0 because nothing is there above it. So pressure head is 0. So total head is how much? 10. So head loss is 0. Head loss is 0. Head loss is 0 now. At the point 6, at this, we have elevation head as 6, but the pressure head is this much. The pressure of the water column above it 4. So pressure head is going to be 4. So total head is 6 plus 4, 10. Now also there is no head loss. Now let us come to the point 2. We will come to the point 3 later. That's A point later. Let us come to the point 2. The point 2, we are considering that when the water passes through this soil, all of the head is lost. All of the head of the water head is lost. When it enters from entry to exit within the soil, all of the head, all of the energy is lost. Okay, so we are considering that at the point 2. Okay, so we know at the point 2 our head loss is going to be the maximum. This total head is going to become 0 now, because we are considering that all the head is lost. That means our head loss is going to be 10 now, because all the head was lost. So obviously elevation head plus pressure head becomes our total head. So obviously pressure head is going to be what? -2. Has to be -2, right? Pressure is going to has to be -2 to make the total head is 0. Similarly, at the 0, what is the elevation at 0? Now here also we are considering the total head is 0 obviously. Okay, head loss is 10, so this pressure head will be 0, 0, 0, 0. Now let us come to the point 3, this A point. Now A point, in the soil, what is my hydraulic gradient I? A head of, how much head is lost? A head of 10. Here it was 10, here it is 0. Here it was 10, here it is 0. Right? Total head at this point, total head was what? 10. At this point, total head is what? 0. So 10 minus 0 by the length of the flow. Length from here to here means what? How much? 4. This 10 by 4 is my hydraulic gradient. So this is my hydraulic gradient. So now, therefore, now, what is the head loss when the flow is happening from here to here? From here to here. When the flow is happening from here to here, how to find out the head loss? Nothing but the hydraulic gradient times this length will give us the what? The head loss. So what is that length? 3. So 10 by 4 times 3, which is nothing but 7.5 meters. So the head loss at point 3 is 7.5 meters. Right? So what is the total head now here? Obviously the total head is going to be was 2.5. Then only my head loss becomes 7.5. So if this is total head is 7.5, the pressure head is always going to be minus 0.5. So that's how you need to back calculate it. That's how you need to back calculate it. So now this way you calculated the elevation head, the pressure head, the total head at all the points, all the required points. Okay, I hope you understood this point. The head loss we calculated first. The head loss, obviously total head is going to be what? From 10 it is coming to, head is becoming 7 head, so how much should be the total head? It should be obviously 2.5, so that head loss becomes 7.5 here, right? So 2.5, so and if the total head has to be 2.5, the pressure has to be 0. minus 0.5. Okay, you understand? Now the second part of the question was, we need to find out the superficial and the seepage velocities. The superficial and the seepage velocities. Now first let us find out the superficial velocity or the discharge velocity, which is V. So V again similar, K into I. K is what? K is given in the question 0.1 centimeter per second. Also porosity is given as 33%. Right. So K into I. So K is 0.1 times I is nothing but 10 by 4. Will give us 0.25 centimeter per second, which is our superficial velocity. Now next we need to calculate the seepage velocity. The seepage velocity will be what? V by N. So 0.25 by 33% it is given. So 0.33 will get 0.7575 centimeter per second. So this way we get the velocity, the superficial velocity and the seepage velocity. Similar to this problem, I urge you to solve, I request you to solve these two here, which you solve it as a homework, and in the next class also we will be solving this again. Okay, just you try to solve that by yourself once. Okay, only then we will be solving that in the next class. Okay, so I hope this problem was clear. So I will repeat once again for your convenience sake. So first at the top point we know elevation head is 10, elevation head is 10 and pressure head is 0 because nothing is above there. So pressure head is 0, so total head is elevation head plus pressure head becomes 10. Head loss is 0, no point of head loss here. Now again I come to this level 6 here, elevation head is 6, total head will be, the pressure head is 4 because you have a 4-meter high water column above it, so pressure head is 4, 6 plus 4 10, again head loss is 0. Now when we come to this point 2, we consider that all of the head is going to be lost while the water traverses through the soil column. All of the head is going to be lost as the water traverses through the soil column. So obviously now all of the water head is going to be lost, so the head loss now is 10. So total head will be 0. So if the total head has to be 0, the pressure head has to be minus 2 because I have an elevation head of 2. Total pressure head has to be minus 2 because elevation head plus pressure head becomes the total head. Right. Now next at the 0 level, obviously everything is 0. It is 0. Head loss is 10. Right. Now next come to the point A. For the point A, I need to find out the hydraulic gradient first, which is 10 by 4. Now when the soil traverses a distance of 3 meters from 6 to here, how much head loss is happening? So nothing but I into 3, 10 by 4 into 3, 7.5. So 7.5 meters is the head that is lost while traveling from point 6 to point 3. While traveling from point 6 to point 3, 7.5 is lost. So my head loss is 7.5. So obviously my total head has to be 2.5. So that my head loss becomes 2.5. Becomes 7.5 now. 2.5, I got this, right? Now I know the elevation head here is 3 meters, so obviously my pressure head has to be minus 0.5, so that my total head becomes elevation plus pressure head plus it becomes 2.5. Okay, so this is how we need to solve this problem. Similarly, you try to solve this case 2 problem, we will see it in the next class. Okay, so I hope everything was clear in today's session. So first we discussed about all the topics about compaction. We studied about compaction, we solved some problems on compaction. What is we saw what compaction is, we saw the compaction curve, how to get the compaction curve, how to get the optimum moisture content, how to get the maximum dry density, all those things we saw. And then next thing, we saw what we introduced the topic of permeability. Okay, permeability. So we saw what is permeability, and then we solved some problems of permeability. Okay, so I hope that all these things were clear to you. If you have any doubt, please feel free to reach me anytime, write to me, mail me anytime, and I will try my level best to solve all your doubts and solve all your issues. Okay, so thank you so much for attending, and we already have also have 5 minutes remaining on the clock, so I will be here till 8 o'clock, 5 more minutes. So if you have any doubt, you can ask me, else you can leave. The class is done, the class is over, all the problems we have solved, but I will be here till 8 o'clock. If you have any doubt, you can ask me. Okay, I'm here. So we'll see you in the next class. That will be on the 17th of February, same time, 17th of February, Monday, same time from 6 to 8 p.m. And I hope to see all of you at the next session. And if you have any doubt, please feel free to reach out to me. And yeah, so thank you so much for attending. Thank you. Huh? The class is over. We have solved all the problems. We will solve the rest of the problems. We will discuss more topics in the next class. The class is over. Thank you for attending. And if you have any doubt, you can ask me. I am here for 4 more minutes. Else, if you don't have, you can leave. Okay.